Welcome to the beginning of Module 2, Electrostatics. This continues on in some ways from what we did in the last module. We're going to continue to deal with voltage in particular is a huge concept. Charge is a huge concept. But now there are no wires, there are no resistors, there are no batteries. There is an electronic component. Well, we'll do a smidgen of that left. There is one electronic component, the capacitor, which is a huge, huge part of this module. I would say the capstone of this is deeply understanding capacitance. But what? But we're taking things into free space. As it turns out, voltage exists. Voltage exists even in the absence of a battery. Voltage can exist in outer space as long as you've got any one charge sitting somewhere. And in Module 3, I'll introduce to you that you could actually have voltage in outer space with no charges around at all. That's way in the future, though. Okay, so, I do have a warning here. The biggest questions that I saw missed on midterm 1 were things where people are leaning on, oh, V equals IR, I could plug in a number, and not interpreting what V equals IR means. Oh, V cross B, I know how to do right-hand rule. Oh, but they didn't use Q. Actually, I think over half of the people forgot to use Q in QVB. It's an electron, you didn't flip it. So what? So this module doesn't actually have a bunch of new concepts, but it has a fair number, and there are equations linking all of the concepts to all of the other concepts. There are a bunch of equations. There are a bunch of equations. And if you catch the pattern behind them, if you understand the principles behind them, there are only a couple of equations and some principles to knit them together. If you let your eyes glaze over when I'm explaining how to interpret crap, how to think about things, how to get a gut feeling for things, if you just let that fly over your head and expect to do it by osmosis, you are not going to pass this module. So I warn you very, very carefully. There are, I think it's about 25 individual equations, 25. You can't just memorize this and expect to know what to use for what. You have to understand what they mean. That's why I give all the examples that I do, all these analogies all the time. And I think that a fair number of those analogies are getting skipped over. Yeah, where's the number that I can plug in? No, you can't do that. You will not pass. Let me give a brief overview. Here is a good part of the study guide for your next midterm. I want you to see these things. There is the deep nature of voltage. There is the deep nature of electric field. What is charge? What is capacitance? There are, let's see, well, let's count them. Voltage is defined as energy per test charge. Voltage in a resistor doesn't go away, even though this isn't super common. Voltage in a capacitor is 1 over Q, capacitance times charge. Voltage inside that capacitor is, oh God, what is it? QD over A epsilon, which can also, which is already expressed in the other terms. The voltage around a point charge is KQ over R. Yeah. Is there another one? Electric field. Oh, right. Yeah. Voltage is change in electric field per change in position. Look, 6 different things about voltage. And there are going to be things about field and charge and capacitance. If you rely on equation sheets and I'm going to plug in numbers without thinking about what they mean, you're going to die. You're going to get a 16% because you'll guess the wrong one. If you think about what they mean, it's bleedingly obvious, though, if you develop that gut intuition, that feeling for meanings and so on. I'm not going to fill out the rest of it. We'll fill out we'll come back to this slide. We'll do this at midterm 2 review time, maybe periodically throughout the semester. No, I want to go back and start, give you guys a chance to start a little light and fluffy. We're going to talk about static electricity and how charges move and what charge is, and I'm going to introduce one new concept, the electric field. God, it was the first day of class, right? First day of class, I discussed what is charge. Well, what is charge? It's electrons and protons. And every electron has this thing called negative charge, and every proton has this thing called positive charge. You put them together, they balance out, and they're sort of shielded from the world. We say that's uncharged. There's charge inside every atom. It's just neutral atoms. We don't care about that because they sort of cancel each other. One individual charged particle is a teensy amount of charge. One individual charged particle is microscopic. You may have heard the rumors that electrons are small. Well, duh. Okay. But, and this is a big but, we define a convenience unit. 1C is 6.25. I'm defining 1 coulomb as if I gathered 6.25 billion, 6.25, what is that, quintillion? Charges together, 6.25 quadrillion individual charges together. Their electrical bulk of having all those charges, that's 1 coulomb worth of electricity. Okay, 6.25 times 10 to the 18. Well, Google Form A, let me riddle me this, Batman. If I say that 1 coulomb is 6.25 times 10 to the 18 individual charges, can you tell me with advanced mathematics how many coulombs each individual charge has? Ready, set, go. Google Form A. What is the charge of 1 proton? And don't look it up. You can deduce this from what I just said. 1 coulomb is that many charges. So how many coulombs is 1 charge? Oh, I forgot. Ten seconds left. Oh, for God's sake, I didn't clear the last one. Hey, hold on. I'm sorry. Don't put it in there yet. Don't put it in there yet. I didn't clear last week's form. I'm going to delete the responses. No, I'm going to close the form. Unlink form. Unlink form. Unlink form. And today is 0216. Now I could save them and look at your stuff individual. Okay, okay, put it in again, please. Oh my God, correct answers. I love you. I love you all so much. Mostly. Okay, people are getting it. Most people are mostly getting it. I claim that if I know X foos equal 1 bar, that I can do any mathematical operation to both sides. Is 2 foos not 2x foos not 2 bars? Is half of x foos not half a bar? Can I not stop. Can I not divide both sides by x and say x over x, which is to say 1 foo equals 1 over x bars? This is true for anything. 12 inches equals 1 foot. 1 foot equals a twelfth of an inch. Whoa, said it backwards. 12 inches is 1 foot. 1 inch is a twelfth of a foot. Same thing. So if I divide both sides by 6 1/4 quadrillion, I get the following. 12 eggs in a dozen. How much of a dozen is one egg? It's 1/12. Perfect, Isabella. That's actually how I said it last year. I like the dozen analogy. Okay, so 1 over 6.25 10 to the 18 is, be careful, I had a fair number of people maybe not put parentheses in their calculator. You need to practice calculator skills if you're going to survive. Okay. The charge of one individual particle is 1.6 10 to the negative 19 coulombs. Check in your calculator, multiply them together, you should get 1. I will give you a few problems in the homework on the test. Well, one problem on the midterm, next midterm, here and there, where I ask you about how many individual electrons were transferred, how many individual charges passed through a given point. All you got to do is calculate in the simple units, calculate in coulombs, calculate in our standard, and then convert. If you know that you've got, 5 coulombs, 5 coulombs times 1.6, sorry, times 6.25 times 10 to the 18 charges per coulomb, just multiply. It's a conversion constant. Same thing as feet to inches. If you've got 5 feet, 5 feet times 12 inches per foot is 60 inches. Yeah. So these are conversion constants. I do want to emphasize, by the way, something that I hope is not new information. Electrons are negative. Stay positive. Electrons are negative. So when I say that this is one individual charge, what I really should say is this is the absolute value of one individual charge. The charge on a proton, QP, is 1.6 10 to the negative 19. Charge on an electron is negative, you guessed it, 1.6 10 to the negative 19. Okie dokie pokey pony? Like sort of bleedingly obvious, yeah? If you are asked to convert a given amount of charge to a given number of electrons, would you put in a positive or a negative number of electrons? What does it make sense to do? How many electrons are, hold me up -3 fingers, please. If we count things, cut off your fingers. Ew. No, don't do that. Always, if I am counting how many electrons, that is different from what is the electrical charge of blank electrons. The charge could be negative, the number is never negative. Because you can't hold up -5 fingers. If you've got -5 electrons, that doesn't make any sense. Yeah, Selena. No, if I've got a number of coulombs worth of electrons, yeah, the charge is negative, but the coulombs worth of electrons divided by a negative charge per electron doesn't tell you how many electrons. Doesn't make sense to use. If I give you an absolute value for the charge of electrons, use the absolute value of the charge of each electron. So far, so good? Do you remember, let me get a show of hands, do you remember coulombs? We didn't do much of charge in the last chapter. Okay, well, it's coming back with a vengeance. Oh, come on. It's just counting. I mean, really, what is a coulomb? No, watt is power. What is a coulomb? A coulomb ain't nothing but a count. You can count. I can count. Maybe it's inconvenient to count to a quadrillion. The conceptual part, that's not the hard part. Ooh, another question? Oh, that was Issa's. Okay, so next thing. Let's talk about classic piece of information, classic experiment from the God, what, 1700s is you take a cat and you rub it on a glass rod. You may or may not take the fur off the cat first. You take fur, you rub it on a glass rod, and electrons transfer one way or the other. I can't remember which is which. And you're left with static electricity sticking to the outside of the glass rod. What does that static electricity do? Well, if I have two glass rods and I bring them close to each other, what's going to happen? I've got some charge here. I've got an equal kind of charge here. If I bring them together, what's going to happen? What do like charges do? What did you learn in second grade? Like charges repel. Yeah? Opposite charges attract. So what happens if I take the cat fur and bring it near the rod? They'll attract each other very slightly. Okay, so what I typically do with this, what the static electricity experimenters did, is that force is very subtle between macroscopic big honking objects like that. What you would typically do is you would take metal balls, just the slub balls, take metal balls and let the static electricity transfer off onto the metal balls and wipe them on the metal balls. Then the metal balls are dangling from like pendulums, and they will either push towards each other or pull away from each other. So in this case, if I've got two negative charges, I go in and wipe some negative charge over two objects. What's going to happen? What's going to happen? I've got negative charges on one side. I've got negative charges on the other side. What's going to happen? Exactly, they're going to repel. They're going to push each other apart. Incidentally, by the way, I do want to emphasize something about size of, or the number of electrons. Individual electrons, eensy teensy beatsy beatsy. Practical amounts of static electricity in these experiments is nanocoulombs. That's still billions of electrons. But with billions of electrons, the forces are enough to move ordinary sized objects. Billions of electrons. How big is a billion atoms? Can you see a billion atoms? 10 to the 23rd atoms is an ordinary sized block of carbon. Can you see one, what is it? 1 billionth? No, less than that. 1 quadrillionth of a, God damn it, 1 trillionth of a gram? Can't see that? No, 10 to the 23rd atoms is huge. Is ordinary size. 10 to the 9 somethings is stupidly small. The number of electrons might be a big number, but it's still microscopic. You couldn't see it, even if you could see electrons directly. Okay, that's sufficient. 10 to the 9, a billion things, is sufficient to push macroscopic objects around. Electricity is actually relatively, really kind of freaking really strong on the scale of all the forces that you learn about. 10 to the 9 might be a large number, but it's a nano of the unit. A nanocoulomb of the base unit is enough to move stuff practically around. Okay, so that's it. There are 10 to the 9 charges, a billion charged particles, excess charges. How many ordinary sized particles are there? 10 to the what? How many atoms in an ordinary sized sample of stuff? What did I just say? Moles. Moles worth. You are many moles worth. I don't know, 100, 1,000 moles, something like that. This is how many moles it takes I'm sorry, 1 mole of water is about this big, right? You could hold a mole of water easily in your hand. 10 to the 23rd atoms. A billion electrons compared to the 10 to the 23rd power of atoms means that there are only a teensy fraction of the total ball gets an electric charge. What's my point? Theoretically, you should draw the pluses and minuses that are still stuck together, but you could never, ever notice the excess charges if you did that. So we're only ever going to draw in the diagrams that I do, the way I draw these, I'm only ever going to draw the unpaired charges, the excess charges. If I get, say, 3 electrons on each, what are these 3 electrons going to do? Those 3 electrons are going to push each other, and they're going to push each other to opposite sides of the ball. They're not going to have enough energy to leap out of the metal and free themselves into, I mean, usually, they're not going to have enough energy to free themselves and shoot into outer space, but they are going to be pushed in the general direction of the right hand, the far edges of the ball, and there's still a force on them. They'll still continue to push apart a bit. What if I just had one? What if I just had a single piece of metal? Forget two pieces of metal pushing on each other. What would it look like if I took this away? Where would those charges go? Would they group on the left? Remember, each individual charge also pushes on its neighbors. Would they group? No. They want to get as far away from each other as possible. You just got one object with some electrical charges on them. Draw on your paper right now. Let's do more than 3. 5. Do 5. 5 electrons. Draw a circle and tell me if this is a metal ball. Looking at a soda can from the end. Where would the charges go? I'm going to put 5 units of 5 units of negative charge, and I want you to draw where you think they would go. Enter your drawing in the Google form. Oh wait, that doesn't work. Remember, each individual electron shoves its neighbors as far away as possible. So where do you think they're going to end up? Okay, is that enough time to guess, to think about it? The usual thing that I see is people draw this. I can't prove this without calc, but this is actually not the average total furthest distance apart. And the problem is the middle charge is actually closer to these suckers around the outside than it could get if you space them equally around the outside. Remember this, charge in general, unless you're pushing on it with some other stuff, charge in general tries to separate itself smoothly around the outside area of an object. Like a clock. Yeah, exactly. It tries to distribute itself around the outside. Now with round objects, this is trivial. Make the shell on the outside, circle looking at a cross section. What if I have something irregularly shaped? What did I just say about where they distribute? Uniformly around the area. Uniformly around the area. So if I have a bunch of charges smoothly sending themselves around the area, is there more or less area pinched together up at the top or at the bottom? Look, in this region of space, let's draw 2 equal-sized circles, shall we? Here's a circle. How many charges are inside it? 4. Here's a circle of roughly, here's a circle of, here's a circle of the same size. How many charges are inside it? I'd say 5.5, 5 2/2. Yeah? No, not the same. You're encompassing more area if there's a pinchy part, if there's a corner. What shape are lightning rods? Are they smooth? Are they rounded? The entire point, pun intended, of a lightning rod is sharp points gather electricity together, electrical charges together. The point of a lightning rod is not actually just to catch the lightning. It is to dissipate the charges that make a lightning strike happen in the first place. And the way it does that is by gathering charges together to make a very intense electrical effect near it, and that will allow some of the charges to spray off the end, diffusing the cloud area around it. Then if there is a lightning strike, of course, it will prefer the nice path instead of down through your building, flammable wood structure, whatever. Yeah, there's that too. But a lightning rod, the whole point, pun intended, of the lightning rod is by concentrating charges of the opposite sign to the cloud close together, where you actually get enough that you can start spraying charges out of the metal into the air around it, starting to defuse. Kind of cool, huh? Did you know that you can actually put metal in a microwave? You can. And turn the microwave on. And not blow it up, even. I have baby food containers that have a metal top, and you peel off the lid part, and it says put it in. There's still a ring of metal. It's a round, smooth ring of metal with no edges or points, and it microwaves just fine. The electrical effect of the microwaves teasing the electrons inside doesn't cause sparks, arcs, damage, explosions. You put a fork in the microwave, the electrical effect of the radio frequency energy inside there is going to make a lot of ionization. There's going to be sparks. There's going to be bad stuff happening, maybe fire. Hey, by the way, don't just go putting random objects into the microwave to find out whether I'm lying to you. I promise I'm telling you the truth. You can Google it, by the way, if you like. A rotten egg? What?
No, I said or an egg.
Yes, 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 yes. Okay. So there are some hopefully useful facts. I will test you on some of these about the nature of charge. Opposite charges attract, like charges repel. Let me go back to the simple example of just a simple shape, no pointy. Let's just talk about, I got a metal rod. And let's say that I don't have a bunch of pluses and minuses. I don't have excess pluses or excess minuses on this metal rod. Okay. But I can bring in another rod with some charge on. Let's do that. Let's imagine bringing in a nearby charge. Hell, I'm just going to draw a big honking plus out there. Bring something in with a bunch of plus charges in there. What's going to happen to the electrical charges inside the rod? Opposites attract, like charges repel. The rod itself is neutral, but just being neutral doesn't mean it doesn't have plus and minus in it, right? What's going to happen to the electrons in the rod? They're going to be attracted. What's going to happen to the protons? They're going to be repelled. Now, the electrons are the things that move in practice. They're teensy, tiny, eensy, weensy, little bitsy. They will distribute themselves uniformly around the facing surface, trying to get as close as possible to their things that they find attractive. On the far side of the rod, remember, they will get as close as possible. The plus charges that are left behind are from the opposite end. This isn't really a great perspective drawing. Plus charges, it's an equal number. I tried to draw an equal number of charges are going to be left on the opposite end. This object is what we call polarized, by the way. Write that down. It's important. This is a polarized object. What happens if I take the big plus away? They're going to go back, right? These charges are attracted to these charges. Plus and minus attract each other. If I've got a polarized metal object and I take away the polarizing external charge, I take away the thing that's driving the pluses and minuses apart, they are going to be pulled back together. What if I get angry and I take my scissors and I cut the rod apart? Grr! I hate this fact that they can get back together, unlike me and my ex. Yeah? What would happen? I'm going to separate the two sides of the rod. I make a slice. Wait, will this do? No, this won't do what I want. If I then separate the sides of the rod, oh, come on. Will this do what I want? Please do what I want. No, I know how to make it do what I want. Jesus. Ugh. Haha. Oh, for God's sake. You know what? Life is suffering. Buddha was right. Life is suffering. Okay, what happens? What happens if I slice the rod apart and separate the two sides of the rod? What have I done? Are there pluses that magically appear on the left side of the rod, on the left rod? Are there minuses that magically appear on the right rod? No. No. Still a balance there. You've just got excess pluses being driven away by that guy. Excess minuses still put in the same place by that guy. What happens if you take away the external polarizing charge? Question me.
Have positive charges on that first circle that's empty, and then negative on the next circle.
Wait.
So we had negative, and then
Those are the ends of the cylinder, by the way.
but where it got cut.
Slice it off, yeah.
Because I'm thinking it like
Magnets and electricity don't behave the same way. Magnet, you cut a magnet in half, each side will still have north-south. Not charges. You're not introducing new electrons, positrons. Yeah, metal rod, cylinder, just baton, whatever. Okay. What happens if I remove the polarizing object? The pluses and minuses will spread themselves out uniformly over the surface area of the remaining rod. Hey! Look what I've done. I have taken an uncharged object. I never touched it with my external charge. And I have caused there to become two equal and opposite, equal number of charges, opposite sign of charges on two separated objects. This is called charging by induction. And the steps for charging by induction are polarize, slice, separate, right? This is what we did. We polarized it, we sliced it apart and pulled them apart, and then take away the external charge, and you're left with two equal and opposite charged objects. Yeah, I guess slice and separate are sort of kind of the same thing. Break. Maybe we should say 3 steps. Polarize, break apart, and then remove the external polarizing. Do you see this? Does this kind of make sense just based on opposites attract like charges repel? I want to emphasize again, there's another thing that I said briefly, the plus charges rearrange themselves. That's a lie. The plus charges don't move. The protons, the rest of the atom is so honkin' big compared to the rest of the ion is something like an atom is like roughly 1,000,000 times more massive than an electron. So what's actually going to happen is you had bare atoms missing an electron here, and then the rest of these atoms had an equal number of electrons around them. You're actually just splitting some of these paired guys off over here to sort of get a balance of unpaired. The pluses don't actually move. You need to know that. Pluses are basically fixed in place just by a mass ratio fact. You can rely on this. I will ask you homework questions and test questions, by the way, about how if I rub a rod on a cat and I take it away and the rod is negative something, what happened? Did we go rod to cat or cat to rod? The stuff that moved is cat to rod. Negative things moving from cat to rod. If I rub a balloon on my hair and later measure my hair as positive, what moved? I didn't put positive things on my hair. The rubber took the negativity away, leaving the positivity behind. So far, so all pretty damn simple. There's one more conceptual thing that I need to introduce that should actually, hopefully, be pretty damn simple too, and that is a conductor versus an insulator. I wish to point out that these are not opposites. You can have different things beyond conductors and insulators. You can have superconductors, which are perfect conductors. You can have semiconductors with a variable amount of conductance. But for the sake of 112, we can keep it simple. A conductor is a swinger, and an insulator is monogamous. An insulator, the electrons and the rest of the atoms love each other so much that the electrons are not going to get divorced from their atoms. Certainly not going to go gallivanting around at the nearest electrical orgy. Huh? Electrons and protons, the electrons and the rest of the atoms stick together, and this proton and this electron are bound. Conductors? Free love, man. Wait, that's the Richard Nixon thing. What do hippies do? What's the hippie thing? Is it this? Yeah, just this? Yeah. Oh God. Whatever. I can't remember anything. I wasn't alive at the time either. So free love. Now, everything that I was describing before with a metal rod, I'm talking about conductors. I was talking about charges moving, freely moving throughout the bulk of the object. Individual conduction shell electrons are not stuck to individual atoms in metals. They are free to move, free to flow. Incidentally, this is also why metals conduct heat very easily, why metals are shiny, why metals are good for electrical conductivity. These facts all go together. It's because the electrons are easily moved from one place to the other. Okay, so conductors, swingers, free love, insulators, monogamous, they are tightly bound. That's not to say, by the way, that you can't break up an insulator. Everyone has their price. There's no such thing as perfect true love. If you shock an insulator hard enough, you can ionize anything. Or you can smear excess charges. Say I rub a balloon on my hair. The balloon's not a conductor, but I can drag positive or negative charges. I forget which way it goes. I could drag negative charges one way or the other and deposit them on the surface of the balloon. The thing to know about excess charge when you've got a insulating surface is charges stick where they're put. So everything I said before about a metal rod and how charges rearrange themselves on the surface, that's true for conductors. An insulator, they can't move around. They're not free to. I mean, that's the whole point of an insulator. So far, so good? You like? We're almost done. We're really almost done. I should actually write more than just this. Electrons free to move. Electrons bound to individual electrons bound tightly. And complete sentence from atom to atom. Hey, who knew this stuff about what makes metal conduction before? Conductor and insulator. Only a couple of people. Okay, yeah, that's what makes a metal. Makes an insulator an insulator. A conductor a conductor. Okay, but you've all heard of conductors and insulators. Yeah, this is the third grade words, right? What's an example of an insulator? Do you guys know stuff they put inside walls? Yes, yes. That is designed very particularly to be a heat insulator. I'm talking about electrical insulator. That's also an electrical insulator. That's not the default thing I want you to think of. Glass. doesn't conduct electricity. Rubber doesn't conduct electricity. Wood conducts electricity a little bit, but not very well. Human body parts, depends on if you're touching the warm, squishy insides or the outsides. Our skin is a crappy conductor, unless it's summertime and you're sweaty. You poke electrodes inside the skin layer, and our warm, squishy insides definitely conduct electricity. Maybe that's a little gross to think about. We'll talk about that actually. That's important for talking about electrical safety, knowing how and why some shocks are dangerous and other shocks aren't. Okay. So, prototype, important examples of conductors. Conductors, just think metals, insulators, glass, rubber, stuff like that. Non-metals. The last thing I wish to discuss today is a new thing called electric field. Electric field and its relationship between last semester's concept of force, electric field, and its relationship between last module's concept of voltage is hugely important. Let me write down a four variable diagram. And I should label this because you don't know all the letters yet. Come on. We will see this diagram multiple times. The faster this clicks, the connections click for you, whoa boy, this is probably the single individual thing that if you see the connections, makes 25 different equations turn into 6 different equations. Last semester, you saw force. We did force up the wazoo. Potential energy. Didn't do that nearly as much, but you saw it. This semester, we spent a bunch of time on voltage. What we haven't done is, well, I know what we're doing now, is electric field. All 4 of these things are related very closely. I will go ahead and put the electric field relationships on now, and we'll come back to the others. Force and electric field. This is what I would call the defining equation. I will put this on midterm too, like probably exactly this question. What is the defining equation for electric field? There are going to be 5 different equations that you see. E on the left side, this is the one and only one that is the central idea that is always universally, forever, uniformly true. Electric field is the force on a charge divided by the amount of charge there. So if you want to know what the electric field is somewhere, oh, take a little bit of static electricity, hold it up, measure the force that that little piece of static electricity is feeling. The electric field is the force divided by however much charge you use to test it. That's not that bad, right? Voltage and electric field are also intimately related. If I know how much voltage there is somewhere, the electric field, the electric field is, do you guys remember force times distance? What's force times distance? Oh boy, that chapter was a lot of work. Work. Force times distance is work. Force times distance is work. If I rearrange this equation, field times distance is voltage. Force times distance to field times distance. These are intimately related. Oh, force and field are connected together. They're all connected, man. Everything's connected. There's a grand conspiracy with the lizard people to make physics simple if you just look for the patterns. Learn from the lizard people or something. Maybe they're supposed to be bad. I don't know. The Illuminati lizard people are good? Whatever. Whatever. If you internalize these two ideas, you will be well on your way to understanding what electric field is. Now, let me put it not just in terms of connecting it to what you've seen before, but in simpler terms. Electric field is the Jedi force emitted, caused by, exuded, sprays out Okay, I challenge you, Google question B. I have defined, this is the core central most important equation that is always true. Electric field is force divided by test charge, force divided by the charge feeling that force. I challenge you to look at this verbal description and fill in the blanks. Give me an equation. How much force does a charge feeling a field experience? Google form B. Fill in the blank. So far, so now I'm looking for an equation. Take the definition, the defining equation, and rearrange them. And check your algebra. You must do the same thing to both sides. Okay, I've got like 5 people breaking the laws of algebra. Hey, turn to your neighbor, please, and check them. Tell them what thing you do to both sides of the previous equation to solve for force. Okay? Check each other before you wreck each other. Solve for force. The answer is if I want to get force out of this equation, I need to eliminate the downstairs. How do I get rid of a fraction? I multiply both sides by the downstairs. If I multiply the left and right by Q, I get the force on an electric charge is the magnitude of charge there times the electric field. And here, this is nothing but an algebraic rearrangement of what I wrote before, but I claim that here is the big idea behind field. You want to know force? Of course you want to know force. Once you know force, you can apply all of the methods from last semester to understand what happens to stuff. I am going to break I'm going to break the question of how does this charge affect those charges, how do these charges affect that charge, into 2 pieces. This feels some charge created by other charges. This is the feeler. Remember, every force has to do with feelers and dealers? Right? Causes and effects. This is everything you need to know about the thing which feels the force, feels the electrical interactions. E is everything you need to know about the dealers. Once you've calculated E, you don't need to know anything about that which experiences electric field. You only need to know about the things that create, that exude, that emit, that emanate the electric field. Once you know E from the emanators, and once you know Q from the things that feel, multiply, baby, and you're done. Hey, 2 minutes. We're not done yet. We're going to be done early, but not yet. I'm going to give you lots of equations for electric field. Let me start simple. Here is the simplest one, and I think, double check, this is the only one that I ask you for this week. Nope, I do ask you to, but we've got another day to do this. Electric field. Remember, we're no longer talking about circuits and wires and batteries and stuff. I claim that you've got a single piece of electricity sitting out in the vacuum of outer space. There's still voltage and field and force and stuff potentially around it. Okay, so I'm going to say here is a point charge. That is to say, I don't want to talk about complicated sizes and shapes. I'm going to just put all the electricity at one place and call this a point charge. The electric field at any other point around, there doesn't have to be, again, there doesn't have to be a charge here. What did I say a second ago about calculating E? You don't need to know jack about the thing feeling in order to calculate field. You don't need to know what exists here, if anything, to calculate field at that location. There we go. It's a really simple formula. Don't take the picture again. There's a square. Whoopsie. Whew, that was terrifying. 9 billion times the amount of charge in coulombs, that's our base unit. 9 billion times how many coulombs you've got. Coulombs causing divided by however far the point you care about is separated from this, squared. Look at the distance between. It's not that bad. A number and 2 symbols. Yeah. Is this always true? No. This is true for point charges. This is not a universal law of nature. This is true if you have a point charge. It is universally true if you have a point charge, but it is not true if you don't have a point charge. Remember, the last question of the midterm, people got wrong because I gave you a battery connected to a resistor and I asked about its properties and everybody just talked about the resistor. There's a battery too. The battery keeps the voltage constant. We didn't go over it yet. If you want to go over it in detail, come to office hours or ask me on email if you can't make it then. The big trick to the last one that everybody missed was they ignored the fact that a battery is connected to a resistor. Okay, well here, we're going to have lots of different examples of how charge can smear around. If you've got a single point charge all concentrated at one location, point charge, then this formula, KQ on R squared, it holds. If you don't have point charges, this is a lie and you'll get everything wrong. I'm going to call this number 9 billion. I usually call that K, lowercase k. Q is charged like before, remember? Coulombs, it's an old pun. Coulombs, coulombs. And R is the distance between the charge and wherever you want to find the field. Great. Once you find the field, how do you get the force? The thing you usually actually care about? Multiply. Last thing, and I'm going to let you go early. There's a difference between capital and lowercase q here. Both are charge. Both are measured in coulombs. This is that which causes field. This is that which feels field. I will call this, always and forever, source charge. It is the source of the electric field. It is the thing causing the electric field, the source of our electrical effect. I will call this thing, the thing that we could use to test how much electric field we have, the test charge. Lowercase q, test charge, uppercase Q, source charge. How do you know which is which? Well, if I ask you, charge A pushes on charge B, find the force on charge B. Charge B is your test. Charge B is the thing that you're finding the force on. Charge B is what you care about feeling. What is the force of charge A on charge B? Charge A is the causer. At the end of the day, you could always flip what you're focusing on, and you focus on one thing causing at a time. In any particular situation, you're analyzing, finding a F equals QE equation, you need to separate them into causer and feeler, source and test. Okay, I will stick around for questions. I'm going to try to upload this video to What's It, but I'm going to say, let's go early today. Merry Christmas. I love you all. Come on up if you have questions. Oh, is there a question in chat? After we slice, do we have to make sure the halves are a certain distance apart? No, as long as they're far enough away so that you don't jump from one to the other.